Hello everyone. We're on our final segment of Module 14. We're covering pages 513 to 517 and the last on your own questions. So in this segment of the chapter, we're looking at catalysts. And just to review, reaction rates can be increased by adjusting concentration, surface area, and temperature. But another factor that we're going to look at now is the presence of catalysts, which speed up the reaction rate without actually getting used up or consumed in the chemical reaction. So if you look at page 512, experiment 14.2 is outlined, and in this case we're setting up an experiment. I just did it at home and took pictures, looking at the decomposition of hydrogen peroxide, which is this H2O2, when it gets broken down into H2O, water, and oxygen gas. Now, if this was just sitting in a regular container of hydrogen peroxide on your shelf, and we talked about this in one of our previous modules, then the decomposition of this would happen very slowly. But when you add baker's yeast to it, baker's yeast is a catalyst for that reaction, and so this is what would happen. So here in this picture we just have the plain hydrogen peroxide in a beaker. It just looks like water. Then we put a portion of baker's yeast on the top. It basically just sits on the top on the surface area, and then after a short time the reaction progresses quite quickly, producing gas and like a foam on top, and then this is it as it's progressed even farther. If you want to watch a 2-minute or so YouTube video of somebody who taped that separately, the man shows the presence of oxygen gas in that reaction. All right, so one of the things catalysts do is they can lower the activation energy of a reaction, thereby increasing its rate. Now, your figure in your book is a little different than this one, but the point of both the figures is just to show how in a normal reaction, if the activation rate was at a certain level, the catalyst would lower it, creating an easier pathway for the reaction to occur, and they speed up the reaction that way. So there's two types of catalyst that the book refers to. The heterogeneous catalyst, that is one when the catalyst is in a different phase than the reactants, and we'll be looking at an example of that, but by phase they're meaning solid, liquid, or gas. And then the homogeneous catalyst is a catalyst that has the same phase as at least one of the reactants. So here is an example of a heterogeneous catalyst. It's our catalytic converter, and that is something that's found typically in the exhaust system of your vehicle, and it is a solid. It's found in a solid form. And the surface of the catalytic converter is typically a ceramic that has a metal coating, and it's an interesting function that it has. It converts carbon monoxide with a single oxygen to carbon dioxide with 2 oxygen through this chemical reaction. The CO plus the O2, the oxygen gas, forming CO2. Well, what the surface of the converter does is it draws in these carbon monoxide molecules, it attracts them in addition to the oxygen molecules, and then the oxygen atoms are then attracted to the carbon, forming then the carbon dioxide, and the O2 is split up. And that all happens just on the surface of that converter, which is quite interesting. So the catalyst never changes. It just serves as a way of aiding the molecules to come in close proximity to one another. Then our homogeneous catalyst is a little different. First of all, we mentioned that it will be used in the same phase as the reactants. So in this case, our reactants are gas, and so our catalyst would also be found in the gas form. However, as compared to the heterogeneous catalyst, the homogeneous catalyst actually changes the steps that the reaction takes. So in this previous example, this reaction occurs whether or not the catalyst is there. However, in this other reaction, for the homogeneous catalyst, this one would occur without the catalyst. However, by introducing the catalyst, you have a new pathway that's created down here. So let's look at this in more detail. We have the oxidation of sulfur dioxide, that's this molecule here, SO2, and it interacts with O2 to form sulfur trioxide. And this is a spontaneous reaction, but it's slow. However, the rate of it can be increased by using the catalyst of nitrogen monoxide. So when you introduce the NO here, then it combines with oxygen gas to form NO2, the nitrogen dioxide. And then when that is combined with this reactant, which was the same as up here, when that's combined in this pathway, the oxygen from the NO2 is then attracted to the one here, and you form SO3, or sulfur trioxide, and the NO is just like another one of the products. So the NO is actually considered the catalyst in this reaction. It is not consumed. You have the same amount at the beginning and at the end. And so this sort of series of chemical equations is referred to as a reaction mechanism, and it just is defined as a series of chemical equations that tell you the step-by-step process by which a chemical reaction occurs. All right, so let's look at a few on your owns. We're on 14.9, and it says to catalyze the following reaction, and we have C2H4, which is considered ethylene, plus hydrogen gas is forming C2H6, which is ethane. A solid platinum is often used. Is the platinum a heterogeneous or homogeneous catalyst? Well, since these are in gas form and the platinum is in solid, it's considered heterogeneous because they're in different phases. All right, on this on your own, 1410, it says two energy diagrams for the same reaction are presented below. Which one represents the reaction with the catalyst? Well, in this case, it's diagram A, because a catalyst has a lower activation energy. And so since the height of this is lower than the height of this curve here, then this one is the one with the catalyst. All right, identify the catalyst in the following reaction mechanism. So again, we see the hydrogen peroxide here. This is an iodine ion, and you notice that you have the same amount of this iodine ion at the end of the reaction pathway. So this would be your catalyst, and this would be a homogeneous catalyst. So I hope that that is helpful, and that wraps it up for Module 14.